You're at the office party. Everyone draws a name from a hat, but suddenly, Bob shouts, "I got myself." Now, everyone has to start over. Did you know there's a 37% chance this happens every single time? By the end of this video, you'll master the dynamic programming logic to guarantee a perfect draw. Pause, this isn't just a party game, it's a massive combinatorial explosion. For a group of 20, there are more valid Secret Santa assignments than grains of sand on every beach on Earth. Without the knowledge we are about to cover, your computer would literally melt trying to calculate these possibilities naively. Pause, in mathematics, we call this a derangement. It's a permutation where no element appears in its original position. If Alice is index 0, she cannot be assigned to index 0. Simple, right? But how do we count them without listing every single possibility? We'll reveal the logic in a moment. Pause, here's a variable reward for the math nerds. As the group size grows, the probability of a valid draw converges to 1 over e, or roughly 36.79%. This constant appears everywhere in CS. If you're interviewing at Google or Meta, understanding this convergence is a high-level signal they look for. Pause, to solve this with dynamic programming, we break it down. Person 1 has N1 choices for a recipient. Let's say they pick person K. Now, we have two distinct scenarios for person K. Before I show you the cases, can you guess how many subproblems we've created? Pause, scenario 1, it's a mutual swap. Person 1 picks K, and K picks 1. They are done. We are now left with the exact same problem, but for n-2 people. This is our first subproblem in our DP table. But what if they don't swap? Pause, scenario 2, person K must pick someone other than person 1. This is mathematically equivalent to finding a derangement for the remaining n-1 people. By combining these, we get our master formula, S of n equals n-1 times the sum of the previous two results. Pause, most beginners stop here. This recursive code looks clean, but it's a trap. It has exponential time complexity. For a 30-person office, your CPU would be spinning for hours making billions of redundant calls. We need to save our work to move faster. Pause, by adding a simple memoization dictionary, we transform the algorithm. Now, each value of n is calculated exactly once. We've turned a super exponential nightmare into a linear time dream. But can we make it even more memory efficient? Stick around for the final tweak. Pause, the iterative, bottom-up approach is what top-tier engineers prefer. It avoids Python's recursion depth limits entirely. We simply fill a table from the bottom up. For 25 people, this gives us a 25-digit number in a fraction of a second. Imagine trying to count that by hand. Pause, we've covered a lot. From the holiday party redraw disaster to the subfactorial formula and linear time DP implementations. You now know why Secret Santa is a secret door into the world of combinatorial optimization and how to code it like a pro. Pause, remember, these derangements appear in network routing, banking compliance, and cryptography. The next time you're faced with a no self-matching constraint in your code, you'll have the exact DP tools needed to solve it efficiently without breaking a sweat. Pause, if you struggle to turn word problems into DP recurrences, you're leaving career growth on the table. Don't let complex algorithms hold you back. Click the link in the description to join our dynamic programming bootcamp and start coding at a FANG level today.